Today we are going to see process concept, operations on process scheduling. Process concept. An operating system executes a variety of programs. Batch systems, they are called as jobs. Time share systems, they are called as user programs or tasks. Textbooks uses the terms job and process almost interchangeably. Process, program and execution. Process execution must progress in sequential fashion. A process includes program counter, stack, and data section. As process executes, it changes state. The first state is the process being created, that is called as new state. When the instructions are being executed in the process, it is called as running state. When the process is waiting for some event to occur, it is called as waiting state. The process is waiting to be assigned to a process, then it is called as ready state. The process has finished its execution, then it is called as terminated state. So totally we have 5 states for each and every process. This is the diagrammatic representation of process state. A new process comes and it will be placed in a new state. And when the process is ready for execution, it is admitted to ready state. When the process is ready for execution, then it is placed in running state. That is called as scheduler dispatch. Many scheduling algorithms will help to choose a process in a ready queue to CPU for processing. When the process is running, it may be stopped based on any interrupt happens. Then it is placed in a ready state again. The interrupts are nothing but any problems which make the process to stop. Either it could be a failure of the system, or it could be the process requesting some IO devices for input and output operation, or the process needs to execute any functions or modules. So those problems are called as interrupts. Why it is called as an interrupt is the execution needs to be stopped in order to do all this processing in spite of running the program. So when any interrupt happens to a running process, it will be placed in a ready state again. And after the ready scheduler dispatcher will select the process and place it in running state. And the process execution may stop from running state because of some waiting of any IO devices. So after the IO completion, again the process will be placed in a ready state. Then the scheduler dispatch again choose the process and transfer it to the running state for execution of the program. So after everything is executed, the running process will be terminated, and it will be placed in a terminated state by exiting the running scenario. So you have all the 5 types of states available in this diagram: new state, ready state, running state, waiting state, and the final state is the terminated state. Process control block. So information associated with each process: the state of the process, counter, and the program counter. Program counter is nothing but which line needs to be executed is actually made by the counter. So wherever the counter places in the programming lines, that particular line will be executed. CPU registers. Any data related to the process will be placed in registers. CPU scheduling information. When that particular process is scheduled for execution, so that will also be placed in the process control block for that particular process. Memory management information of that process will also be placed in the PCB. Accounting information. Accounting information is nothing but whether the process is completed or not. That information will be placed in the accounting information. IO status information, whether the process has taken any input output, needs any input output, or already requested any input output device. So all those information will be placed in IO status. So the process control block will be created for each and every process that is in running state. So the process control block contains process state number, counter, registers, memory limits, list of open files, and all other things representing a particular process which is running. The CPU switch from process to process. So how actually CPU executes at the time of any interrupt happens for one process. So the CPU cannot be idle. Therefore, it chooses the another process for execution. This CPU switch happens from process to process every period of time. So the processing of CPU, switching of CPU from process to process, how it happens, we are going to see now in this diagrammatic representation. So process P0 and process P1, we have totally two process. And when the process P0 is in executing state, and the operating system will save the state of the process P0 in the PCB not when the interrupt or system call happens when the process P0 is executing. Once the state of the process P0 is stored into the PCB, then it will go for the it will go for executing the process P1. So that time it needs to check the PCB of P1 in order to restore the state of the particular process P1. So after reloading the status, it starts executing process P1. And once any interrupt happens for process P1 is in execution, so now process P1 gets stopped and the state of the process P1 is again saved in the PCB1, and it will reload the state of process PCB0, which is already stored or which is already stopped by some interrupt, and it will continues its executing for process P0. So the time taken for getting the information from PCB, so that time is called as ideal time for the process P0. So we have only two times or two states for the process when it is executing. One is the executing state, another one is ideal state. If the process is an ideal state, it will not do any process. It will not do any execution of lines. So process scheduling queues. So we have three types of queues available: job queue, ready queue, and device queue. What is a job queue? Set of all process in the system is called as a job queue. What is ready queue? Set of all process in main memory ready and waiting to execute. Then device queue is nothing but set of process waiting for an IO device. So the process migration between the various queues happens frequently, and everything is placed in queue. Then only it is executed for further processing. Be taken for further execution. And ready queue and various IO device queues. So ready queue header contains the head and tail information. The head information contains the previous queue header, and tail information or previous PCB header. That is the starting PCB header, and tail information contains the ending PCB, ending process control block, whichever it has. So tail information contains the PCB. So when you see the diagram, you can see that for a ready queue in the first place, you have PCB7 in the head and PCB2 in the tail. And when you go for this unit 0, you can see that the head contains PCB3 and the tail contains PCB6. And it also have in between PCB14. So whenever any process requests the disk, so if the PCB3 requests the disk, then the disk will be allocated for PCB, that is the process 3, and the state will be stored in PCB. And similarly for 14 and 6. And certain devices, they don't have any requisition, like magnetic tape unit 1. You can see that the head and tail is actually not connected to any process, which means this particular device is not requested by any of the process. Representation of process scheduling. So how it happens is from the ready queue. Ready queue is the queue which contains all the process which is in waiting state for getting executed. So from the ready queue, the CPU takes one process, and when it finishes the process without any disturbance, it will be terminated. If suppose while the process is running in CPU, any IO request happens, the CPU transfers to IO request, and that will be placed in an IO queue. IO queue which contains all the process which is waiting for the input output device. And after happens the IO processing, again the process will be placed in ready queue. At that time, CPU will switch to some other process. And when the process is in execution state in CPU, sometimes fork a child happens. Fork a child is it needs to execute a sub process. So that will be sent for child execution. After such child execution completed, again it is placed in ready queue. And similarly, it may happen some any interrupt. When the interrupt occurs, the interrupt signal handling will take place, and the interrupt will be corrected. Then again it is placed in the ready queue. Or sometime if you are using if the CPU is using some round robin scheduling, a time slice will be represented for the process. And if the time slice expired also, the process needs to be again placed in the ready queue. So therefore, all these four interrupts happens for the process to get stopped, and then again it is placed in ready queue and taken by the CPU whenever it needs to execute that process. So this representation is for the list of process which is ready in ready queue for execution. So the schedulers, what is meant by scheduler is from the ready queue, a process needs to be chosen and placed in the CPU for execution. So the process will be chosen by the scheduler for execution. So it has two types of schedulers. One is long term, another one is short term. What is long term scheduler? It is otherwise called as job scheduler. So it selects the job, that is process should be brought into the ready queue. So long term scheduler work is the newborn, the new process which has been entered. So that newborn process will be selected by the long-term scheduler, and it is placed the process in the ready queue whenever it is ready. But what a short-term scheduler is, it selects the process from the ready queue that should be executed next and allocates it to CPU. So that is short-term scheduler work. So, but everything happens because from the ready queue, the process cannot itself go into the CPU for execution. So it needs a scheduler. So all this scheduler itself is a program. Everything is a program which is written in operating system. The work of the scheduler is to select the process and keep it in the place wherever it needs. Addition of medium term scheduling. So sometimes a medium term scheduling needs to be added. The medium term scheduling work is whenever the process needs to be needs to be waiting for any IO, waiting in IO queue, and again it is placed in a ready queue. So there won't be any problem. But whenever the ready queue data is available in any backing store or any process which is partially executed and swapped out, that process needs to be swapped in with the help of the medium term scheduling only. So what is meant by swapping is from the backing store, it needs to be placed in the memory for execution. So that is happening with the help of the swapping technique. So swap in is partially executed swapped out process will be in a queue. So from that, it needs to select that process to complete its execution and place it in ready queue. So what a swap out is, the CPU cannot be able to execute the process for some reason, or it is actually need to be stopped for any interrupt. Then that will be swapped out and placed in the partially executed swapped out process. So this is made by this medium term scheduling. So whenever needed only, we can use this medium term scheduling, or else it is enough if we use the concept what we have seen already, the representation of process scheduling. And the schedulers work is short-term schedulers invoked very frequently, that is within milliseconds, it has to select the process and keep it in ready queue. In the CPU, from ready queue to CPU. Long-term schedulers invoke very infrequently, that is seconds or minutes, maybe very slow. What is the work of long-term scheduler is it has to select the process from the new state to the ready state. So this cannot be happens frequently, because when it happens frequently, the problem called degree of multi-programming is affected. So what is degree of multi-programming is at the same time more than one program tries to be getting executed, but when any problem happens like deadlock, the whole process sequence of process in ready queue, or the whole sequence of process in CPU which is running cannot be completed work. So therefore, all the sequence of process needs to wait or to be aborted. So this problem happens when more than one process is getting executed. So which how many process uh, needs to be placed in CPU for execution is decided by this long-term scheduler. If it controls the number of process entering into CPU, then that is called as degree of multi-programming. Process can be described either IO bound process, CPU bound process. So whichever process needs only the IO processing, IO request, or input output device device uh, to be executed, then that process is called as IO bound process. And CPU bound process is whichever process needs only the CPU for execution, those processes are called as CPU bound process. What is context switch? See, context switch is when CPU switches to another process, the system must save the state of the old process and load the saved state for the new process. So when CPU switches to another process, the PCB needs to be stored. So the PCB saving the state in the PCB for every time when it comes out, or even when it is inside the CPU for execution, then that is called as context switching. So it's a overhead thing, because you imagine for multi-programming more than one process. Imagine that 100 processes running at the same time in the CPU, means every process may request IO, every process may get interrupt. So the state of each and every process at a particular time to be stored may be above 50. So this context switching time is overhead. So the system does no useful work while switching. So if imagine that if the switch system is storing only the context switch details in the system is storing only in the PCB, the context switching will happen. So the information is stored in PCB, but the CPU will be idle without working. So the time dependent on hardware support. So you can even place the time slice for multi-programming to get executed, but it should be supported by the hardware. Cooperating process. So independent process, you have two types of process. One is independent process and another one is cooperating process. Independent process cannot affect or be affected by the execution of another process. So cooperating process can affect or be affected by the execution of another process. So cooperating process needs some communication between two processes. So because it is a cooperation process, if it is an independent process, it doesn't bother about other process execution. Advantages of process cooperation is information can be shared between any number of process. The computation will be speed up. That is, instead of working by simply one process, it has been shared with multiple process, means that at the same time, the work will be completed. So the computation speed up is there, modularity is there. So we are going to divide the modules, and each module will be run by each process, means it is very easy for completing each and every module in the process. So modularity is there, convenience is there. So therefore, cooperating process or usage is very useful than independent process execution. So that has been the cooperating process example has been given here as a producer consumer problem. So what is the producer consumer problem is when the producer produces items that should be consumed by the consumer, and imagine that the producer is producing some 1,000 items for each day, but the consumer cannot sell that or cannot buy that item, 1,000 items for in each day. So what happens is the items are more produced and it is placed in godown, which cannot be consumed by the consumer properly. So therefore, the items will be more and the place for storage will be very less, means you will get a problem. So, or maybe the product gets um, rotten, or you cannot use it for further usage. So similarly, if when the consumer is consuming more number of products and the producer cannot meet the expectation of the consumer, also is a problem. So everything should be in a correlated way. So for that, it is using two types of buffers. One is unbounded buffer and bounded buffer. What is unbounded buffer is the producer can produce any number of items and the consumer can consume any number of items. There is no condition. But what is bounded buffer is the producer will produce every day with a condition of, say for example, he may have chosen only 10 items to be produced per day. Even though it is consumed or not consumed, he will stop production. So that type of production based on some condition is called as a bounded buffer. So whenever you use a cooperating process, the even if you take the example of producer consumer, you have to send some information from the producer to consumer and the consumer to producer, because that information will help the producer to stop the production or to increase the production. The information sent by the producer will help the consumer to understand the production problems, and in such a way to he will or the consumer will choose to use the products in a proper way. So that type of communication between cooperating process is called as the IPC, inter-process communication. So it has some rules and regulations to follow. So mechanisms for process to communicate and to synchronize their actions. So message system is used which process communicate with each other without resorting to shared variables. So process will be communicating with each other through this IPC technique. So it provides two operations, send and receive. A message can be sent from one process to another process, or a message can be received from one process to another process. So if P and Q wish to communicate, they have to first make a communication link between them, and then only they can exchange the messages. It could be either sending or receiving. When P sends message to Q, it is sending. When Q sends a reply to the message sent by P, then it is receiving for the P process. Okay, and implementation of communication link. So the communication could be of link could be of two types. One is physical, another one is logical. If the communication link is physical, that means all the resources will be shared between the two processes. That is, memory will be shared, hardware bus will be shared, like that. Many informations are shared between through this communication link. And what is logical communication link is logical properties. Logical properties were shared between the two resources. So how the links should be established? Before establishing any link, you have to satisfy all the requests, like how the links are to be established. Can a link be associated with more than two processes? How many links can there be between every pair of communicating process? What is the capacity? Whether the size of the message is going to be fixed or variable, whether the link is going to be only unidirectional or bidirectional. Unidirectional is only one process can send the message, the other process can receive it, but it cannot send any messages. So that is unidirectional. Bidirectional is both processes can send and receive the messages. So what is direct communication is the process must name each other explicitly. That is, send P comma message is a command which the OS will understand that send a message to process P. Receive Q comma message means receive a message from process Q. Properties of communication links are established automatically. Exactly one pair of communicating process. Between each pair, there exists exactly one link. The link may be unidirectional, but usually it is a bidirectional. What is indirect communication is messages are directed and received from mailboxes. So each mailbox has a unique ID. process can communicate only if there is a shared mailbox. The properties of the indirect communication link established only if process share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication links. Link may be bidirectional or unidirectional. Indirect communication. The operations made in the indirect communication is a new mailbox will be created, send and receive messages through mailbox, or you can destroy a mailbox. Primitives are defined as send and receive receive command which are being given. What is indirect communication is mailbox sharing. P1, P2, and P3 share mailbox A. P1 sends, P2 and P3 will receive. Then if that is the concept, then which process will receive the message first? For this, the solution is allow a link to be associated with at most two processes, allow only one process at a time to execute a receive operation, or allow the system to select arbitrarily the receiver. Sender is notified who the receiver was. Synchronization, message passing may be either blocking or non-blocking. Blocking is considered synchronous. Blocking send has the sender block until the messenger is received. The sender cannot send the message when the receiver is not receiving. Blocking receive is nothing but the receiver receiver is blocked until a message is available. Once the receiver is opening the message means he may get other messages. Otherwise, he will not receive any message. And what is non-blocking is it is considered as asynchronous. Non-blocking is it can send the sender can send the message and continue to send the message even the receiver is not receiving. And non-blocking receivers the receiver receive a valid message or null. So the receiver will receive continuous valid messages or he may not receive any message. So that is called as non-blocking. What is buffering? Queue of messages attached to the link implemented in one of three ways. Zero capacity, or zero capacity means sender must wait for receiver receiving the message, and bounded capacity is finite length of n messages are bounded. Sender must wait if link full. Unbounded capacity is infinite length. Sender never waits. And the synchronization is nothing but concurrent access to shared data may result in data inconsistency. So data inconsistency is the data will not be properly stored in all the places it needs to store. That is called as data inconsistency. Concurrent access is nothing but at the same time more number of process get accessed. Maintaining data consistency requires mechanism to ensure the orderly execution of cooperating process. And shared memory solution to bounded buffer problem allows at most n-1 items in buffer at the same time. The bounded buffer problem of producer consumer is we are defining in this code, in this pseudocode, you can see that we are defining the buffer size as 10 as a constant number, and the items will be stored until the buffer size. So therefore, only 10 items can be stored in the bounded buffer. And the producer process is, it will check the item next produced, while counter equal to buffer size means you cannot produce any item because maximum number of items production is reached. That is, in the case of our pseudocode, it is 10. So nothing will be done. But if while the counter is less than buffer size, what is the counter is nothing but how many number of items we have produced. So in order to find that, you are using a counter. Initially, it is 1, and when one item is produced, then the counter will be incremented. So buffer of in equal to next produced, which means the next produced item will be stored in the buffer array. Then the buffer, the in will be incremented. So in the next, the pointer will point in the memory to the next position. For that, we are incrementing in equal to in plus 1. And in is the variable used in the producer problem, because the producer is going to produce the item and place it in the buffer. So then only the consumer can consume the item from the buffer. So it is using the variable in producer process, and the counter is incremented. And when it comes for the consumer process, it will check for the counter. If the counter is 0, means no item has been produced. But otherwise, it will consume the items which is stored in the buffer with the help of a variable out, array variable out. So buffer of out means that will store the first value that is consumed, that is already produced by the producer, and it will store in the next consumed. So the consumer can consume the item from the next consumed variable, and the out will be incremented because we need to check whether the out is trying to access out of the array size, that is buffer value. The buffer value is 10. So the consumer can access only until the buffer reaches 10. So after that, if he is trying to access the 11th item, it is not possible. And the counter will be decremented in order to say whether the consumer has consumed all the 10 items, the counter is used here. The statement counter plus plus and minus minus must be performed atomically. Atomic operation means an operation that completes in its entirety without interruption. So when any interrupt happens, the counter value gets changed. So the producer problem cannot be executed properly. So the bounded buffer, the statement count plus plus may be implemented in machine language like this. So even though you give counter plus plus, the value of the counter will be stored in the register. Inside the memory, it will be stored in the register. So register 1 equal to current counter value is stored. Register 1 equal to register 1 plus 1. That means the register pointer is moving to the next register in order to store the next counter value. So now the register value will be stored in the counter. So when the counter in the producer problem gets increased, the next location where the register is pointed in the counter, in that place, the produced item will be stored. And the statement count minus minus, that means register 2 will have the counter value of the consumer. And whenever one item is consumed, the register needs to be moved to the previous register. The pointer of the register needs to previous register. That's why we are decrementing one register, and the current register value will be stored in the counter variable. So bounded buffer is nothing but if both the producer and consumer attempt to update the buffer concurrently, the assembly language statements get interleaved. So only when the producer produced the problem, the consumer can consume it. Otherwise, the consumer cannot consume it. So if both the producer and consumer trying to access it simultaneously, so the assembly language statements cannot be executed properly. So interleaving depends upon how the producer and consumer process are scheduled. So bounded buffer is assume counter is initially 5. So one interleaving of statements, if anything happens, the value of count may be either 4 or 6, which is not the correct result. So therefore, the interleaving should not happen between accessing of bounded buffer, a problem of producer consumer. If interleaving happens, that means trying to access simultaneously both the producer and also the consumer. So if this interleaving happens, the results will be the wronger one. What is race condition? The situation where several processes access and manipulate shared data concurrently. The final value of the shared data depends upon which process finishes last. So when several processes getting executed at the same time with the shared data, whichever process finishes at the last is the final value of the shared data. So this race condition needs to be prevented. So for that, concurrent process must be synchronized. What is concurrent process? Parallelly running process or called the concurrent process. At the same time, many number of process gets executed, then it is called as the concurrent process, which will prevent the that should be synchronized. Synchronized means not all the process will access the shared data at the same time. So if it happens, the race condition will occur. What is race condition is continuously the process or more number of process trying to access the shared data. So no process will be allowed to enter into the shared data, or no process when one process is executing that shared data, all other remaining process needs to wait for a long time. So this is called as a race condition. This should be avoided with the help of synchronizing the concurrent process. Critical section problem. So n process all competing to use some shared data. So for this, you have to use a code segment called critical section in which the shared data is accessed. The problem is ensure that only one process can access the critical section and no other process will be allowed for executing at that particular point of time. So the solution will be either you use the mutual exclusion concept. Mutual exclusion is if process PI is executing in its critical section, then no other process can be executing in their critical section. Progress is if no process is executing in the critical section means the process can be enter into any process which is requesting the critical section can enter into the critical section, and the selection of the process it should not be postponed. That means once the critical section is free for execution, immediately the next process waiting for the critical section will be allowed to enter. And what is bounded waiting is a bound must exist on the number of times the other process are allowed. That means if the same process is allowed into the critical section for number of times, then other process needs to wait for a long time. In order to avoid that, you have to set a value that at a particular time or a process can enter into the critical section only for the bounded value time. If it is 10 times means one process can access the shared data only for 10 times. Assume that each process executes at a non-zero speed, no assumption concerning relative speed of the n processes. And this is the diagrammatic scenario. Only two processes we have P0 and P1. The general structure is do entry section. That means the process now entered into the entry section. It is ready to enter into critical section now. So once the process already in critical section is executed and went into the exit section means the next process can be scheduled for the critical section. Once the process enter into exit section, the work of the critical section is over for the process. So we can do the other reminder sections that needs to be executed and give the process to the reminder section. So every process, please ensure that every process should enter into the exit section and reminder section in order to complete its process. Even though it has accessed the shared data in the critical section, the reminder sections can also be completed. Then only you can allow the process to go out of the critical section. This happens for each and every process. That means if you are having two processes, when P0 is in critical section, P1 is not allowed into critical section. So when P1 is in critical section, the P0 will be in exit section or reminder section, right? So at the same time, when P1 is in a critical section, we cannot be able to allow the P0 into the critical section. So as we are having only two processes, we can say that when one process is in critical section, other process will be in reminder section. Semaphores. So for this critical section problem, a semaphore variable is used. So semaphore S is a variable, it's an integer variable, which is going to do the synchronization. So it is accessible only through two atomic operations. So one is wait, another one is signal. So S is the semaphore used in the atomic operations wait of yes. That means when one process has received a signal of wait of yes, then the other process which is requesting that semaphore will wait until this process gets completed. So while S less than or equal to 0, that means no process is there, do no operation. When any of the process is in S semaphore variable, then do the process and decrement the S value. So after completing for one process, the operations, the critical section operation, signal is made for yes, through yes. So that means the next process can enter. So the S will be incremented, the signal will be incremented and sent to the other process. So other process can enter into the wait of S now. So similarly for each process, a wait and signal atomic operation is executed. Critical section of N process. So shared data, semaphore, mutex. We are going to use the mutual exclusion variable, that is mutex.
Initially, it is 1, and process PI is entering. With the mutex, you are doing that atomic operation of wait of mutex. So when the mutex variable is in waiting state, other process will not enter into the critical section, which means one process is now executing in critical section. And once the process in critical section is gets executed, the mutex will be with the mutex variable. You are giving the signal. Then the process in critical section will go into reminder section, and some another process can be allowed to give the weight of mutex atomic operation. This will be executed for all the process in queue. Semaphore implementation. So you have given a value and a process star L. Star is the pointer. So that means more number of processes. Pointer is actually accessing the process from the memory directly. And the value of the semaphore is stored in the variable value. Two simple operations, block and wake up. So this operation helps in suspending the process that invokes it. And wake up P resumes the execution of a blocked process. For some reason, if any process is suspended, that can be again raised up with the help of wake up command. So these are other two simple operations. These operations are actually it is executed only when it is needed, but wait and signal is the most important operation that should be executed for each and every process. So semaphore operations now defined using waiters and signalers. The complete operation working is given in this wait of s. Blocking happened, block with the block command, and in the signal process, once the blocking works have been done by the process, it should be waked up. So therefore, the wake up is called in the signal process. Semaphore as a general synchronization tool executes B in PJ only after A executed in PI. Use semaphore flag initialized to 0. So you can see here PI, PJ, two process. A is executing. See, the condition is execute B only after executing A. So therefore, in PI, A is executed. That means the flag variable is used and it is applied for the wait operation. So therefore, the B in process PJ is going to wait because A should be executed first according to the condition. So therefore, B is now waiting with the flag variable. And once A has completed its execution, it will give the signal flag. So automatically PJ will start its execution for B. So this is the synchronization tool. This is a synchronization tool that is semaphore. So we have seen for semaphore, S is the variable that is used with the operation. Even you can use the flag variable for blocking the process and executing the process in critical section. So the semaphore can be any variable. It could be yes, or it could be any flag variable also. But if for every thing, the process, when the process should be controlled, entering into critical section means you have to use the semaphore concept. And what is deadlock and starvation is when you use the semaphore tool, two or more process are waiting indefinitely for an event that can be caused by only one of the waiting process. So if the two or more process is waiting for the same thing, say for example, the P0 and P1, P0 is waiting for S and P1 and is requesting for Q, but P1 is but it is having the Q. The signal is not has been given by P0 for Q, but P1 is requesting Q, so it is waiting for Q, but the signal is given for P0 is the signal is not given for P0 for yes, which means P0 is waiting for yes and P1 is waiting for Q. Both the variables or semaphore variables are actually blocked by P0 and P1. So therefore, none of the process is going to get executed. Only when the process P0 gives signal for S and only when the P1 gives signal for Q, both process can get executed. So now in this situation, both process P0 and P1 is
waiting as a deadlock. That means no process will be executed and complete its execution. So this type of indefinite blocking makes the starvation. That means the other process cannot be enter into the critical section because these two processes are still waiting in a deadlock state. So the solution for this is any one of the process needs to be removed from the semaphore queue. Then only the other process gets executed and make way for the remaining process to get executed. And two types of semaphore is there. Counting semaphore. So you have an integer value which can range for over an unrestricted domain. And what is binary semaphore is integer value can range only between 0 and 1 and can be simpler to implement. So can implementing a counting semaphore? Yes, as a binary semaphore. Implementing S as a binary semaphore, the data structure is S1 and S2 are the two variables, and the initialization is S1 equal to 1, S2 will be definitely 0. If S1 is 0, S2 will be 1. C equal to initial value of semaphore, yes. So wait operation is, the C is a variable. In that previous example, we producer consumer problem, we have used counter as a variable, and here they have used the C as a variable. And if C is less than 0 means you have to allow the process to enter. So signal S1, now S1 enters the critical section, S2 will be waiting. And once S1 gets completed, the signal will be sent by the S1 so that that will be sent to S2. Now say S2 will be executed and S2 gets completed, S1 will be given the signal by S2. So the classic problems of synchronization. So we have three example of problems that in order to show the synchronization needs to be done in a proper way. So bounded buffer problem, readers writers problems, and dining philosophers problem. Bounded buffer problem is the shared data is used, that is a semaphore, full, empty, or mutex, and initially full equal to 0, empty equal to n, mutex is the variable, that is semaphore variable. And bounded buffer problem for producer consumer is produce an item in XP, weight of empty, weight mutex. Weight of empty is now the production is happening. So definitely there won't be an empty that is going to be filled. After that, add next P to buffer. There is next process to the buffer. A signal is given in for mutex also, and also the signal is full. That means the producer has produced an item. So again, he will produce the next item. So similarly, if he has a bounded buffer, until the bounded buffer value reaches, the producer will be producing the item and placing it in the buffer. So bounded buffer problem, consumer processes the now the producer has produced all the items and it is stored in the memory. So therefore, the memory is full now. So weight of full is given, mutex variable is weight is given. That means no, only one consumer can access the item in the memory. So other consumer needs to wait. So remove an item from buffer to next C. Next C is the variable where the value is stored. And once it is access the first item, signal of mutex is given and signal of empty is given. That means all the values are consumed by the consumer. Then the mutex signal is given. That means the next process can be done. What is the next process? The producer needs to produce the process. So the consumer will come out and the producer will start its processing. And the signal empty is given, which means all the products has been consumed by the consumer. So until this consumer problem works, the producer will wait. When the producer problem is executing, process is executing, the consumer will wait because of the mutex variable, wait and signal operation. And what is readers writers problem is, here we are going to use the write as the WRT as a variable, read count is the variable used for reading. So that means whenever a reader is reading a material, the writer cannot update the information. So whenever the writer is updating the material, the reader can read the process. So for that, a wait and signal is being used here as a semaphore. Wait of WRT, which means writing is performed. So no reader can enter into the process of reading. So once writing is performed, the signal of WRT is given, so the reader can now enter. So wait of mutex is used when the reader has completed its reading, read count has been incremented. So all the readers, when all the readers has completed their reading, the read count is equal to 1. If the read count becomes 1, that means all the readers has completed their process. So they give signal for writing. A signal mutex is given, reading is performed. So at that time, writer cannot do anything. And once if read count equal to 0, that means all the readers has completed their reading, then the signal will be given to the writer for writing into the process. And the next example is the dining philosopher's problem. Here, the chopsticks are used. 5 renowned scientists are sitting there. Their work is to simply eat. When they are hungry, they will start eating and then they will read. After completing the eating, they will keep the chopstick. So every person will have a left chopstick and also the right chopstick. That right chopstick belongs to the next person, and the next person will treat it as a left chopstick. And similarly, the same way, all the persons in the dining table, which is in a circular design, needs the chopstick. So we don't know which scientist will they take the chopstick and eat when he is hungry. Their work is to think, eat, eat. So this process is continuously done by the renowned person, that is philosophers. So when once left side chopstick of the fifth person is being used, the first person has to wait for his left chopstick, which is used by the fifth person. So a weight needs to be given for the first person. So weight of chopstick I is given. If it is the fifth person, means the fifth person is eating now. So once he finishes his eating, a signal is given. So the next person can start his eating. So after eating, that particular philosopher will go for thinking. So a signal is being made for the first user to access his chopstick. And similarly, for all the 5 users, to use the chopstick, they need a wait and signal operation. If all the philosophers are trying to eat with chopsticks at the same time, 2 persons will not have their chopstick, right side chopstick. So it is a problem. So in order to avoid that, we are using this semaphore variable to make the other person who needs the chopstick of the previous person to wait until the person gets finished his eating. The critical regions are nothing but high level synchronization construct. A shared variable v of type t is declared as shared t. Variable b accessed only inside statement. Region b when b do s, where b is a Boolean expression. While statement s is being executed, no other process can access variable b. Regions referring to the same shared variable exclude each other in time. When a process tries to execute the region statement, the Boolean expression b is evaluated. If b is true, statement s is executed. If it is false, the process is delayed until b becomes true and no other process is in the region associated with b. High-level synchronization. What is meant by monitors is high-level synchronization construct that allows the safe sharing of an abstract data type among the concurrent process. So a monitor is made and the monitor will contain all the variable declaration, shared variable declaration and shared procedures. Procedure body will be P1, P2, Pn up to any number of procedures you can write, and any initialization code you can write in that particular section. And this is the general structure of a monitor. So monitor is also a program what we are writing for making the for making the synchronization problem in a work in a better way. And monitors, to allow a process to wait within the monitor, a condition variable must be declared. That is condition x comma y. The condition variable can only be used with the operations wait and signal. So if you are using x, you can use x dot wait. If you want to use the y variable for giving the wait operation, you can use y dot wait. And similarly for signal operation. The operation x dot wait actually means that the process is invoking this operation is suspended until another process invokes. X dot signal is operation resumes exactly one suspended process. If no process is suspended, then the signal operation has no effect. If any process is executing, a wait will be given with the condition variable x dot wait. That means the other process needs to wait. So if once the process inside the monitor get executed, the signal will be given by the same conditional variable x dot signal. If there is no process waiting, the signal operation is actually not needed. So it has no effect. And this is the schematic view of a monitor. So inside the monitor, you have shared data, its initialization code, all the operation or executions to be done, and all the entry queue is the process that is waiting to access this monitor. And monitor with condition variable is, so you are giving queues associated with xy conditions. You can see there x contains some 3 process, y contains 2 process. That means x 2 variables we are conditional variable 2 variables we are using. So x may have some process and y may have some process. When x is one process is executing inside the monitor, y process need to wait. After the signal given by the x, the y process can enter into that monitor and do the operations. So that time x process will be given a wait operation. So x process cannot enter into the monitor now. So in similar way, we are using the monitors and the synchronization variable, that is condition variables, with the wait and the signal operation. We are controlling the process not to enter at the same time into the critical section region, critical region. So for this dining philosophers example is used. So they can pick up the more modules has been written, pick up, put down, test. Pick up, they are picking up with a chopstick. Putting down, they have finished eating, so they are putting down the chopstick. And test whether the chopstick is available is not or not. That is tested in the test module. And we have to identify the state of each and every dining philosophers. Whether they are in, if they are in thinking state, the other person can use the chopsticks for eating. If they are in eating state, the other person should wait. So in pickup, we are going to find the state. If he is hungry and other process is using the chopstick, he needs to wait. Or if he started his eating and chopsticks are available and he started eating, means one person started eating, means the other process needs to wait. So therefore, that particular process will give the wait signal. And what is put down is, so once they put down, they start, their state will be in thinking state. So once they put down, the neighbors, left and right neighbors can now, if they want, so whether they want the chopstick or not, that is checked in the test module. So if they want, they can use the left and right neighbors. They can use the chopsticks of the person who has now completed his eating. So we are checking the state of philosophers using this test module, whether he is hungry and also he wants to eat. Then a signal will be, once he finishes eating, a signal will be given to the other person. So variables, mutex, next count, or the variables, and the external procedure will be replaced by wait and signal of the mutex variable. So the monitor will definitely use the mutual exclusion concept, that is mutex variable, for its processing. The implementation of monitor is semaphore is declared XM, and the wait and signal will be given by the semaphore XM also. So in the previous process, it has given a wait. The mutex variable has given a semaphore variable has given a wait, and the mutual exclusion variable is also used here in order to give the message to the user. That is, one process is now executing. And similarly, when you go for the signal process, so signal will be given with X and semaphore variable, and the next count is allowed to enter. So this is how the monitor is implemented. So the monitor, semaphore variables, mutex variables, everything is used for making the synchronization work better. Thank you, students.